Hi. Today we'll be talking about rational functions. And we're going to be bringing together what we learned with rational expressions together with algebra and geometry to create something really, really interesting and pretty bizarre. So what are rational functions? Why is there a video on them? And why do we care? Well, rational functions introduce some very, very interesting properties into the world of graphing and algebra that we have to deal with. But first and foremost, what is a rational function? Well, a rational function is, put extremely simply, a function that is a rational expression, which is just a division of two polynomials, right? Something like 2x squared plus 5 over 2 minus x squared would satisfy as a rational function. And it turns out that they have some pretty interesting properties. So let's just say I immediately went on and graphed this function because I was bored or interested or I really just didn't care. Right? When I graph this function, I noticed some pretty bizarre results. This is a weird graph indeed. I have what it seems to be 3 separate lines on this graph, and this is pretty bizarre because this is not a quadratic. This is not a parabola or a cube, or even a square root graph. This is something entirely. There are 3 different lines, and it seems that there are points which this graph seems very close to reaching, but doesn't actually manage to intersect or touch, right? Both vertically, right here and here, and horizontally along this line. It gets really close, but it just goes on for infinity without touching it. It goes on for infinity without touching it. This is what we call asymptotes, right? Oh, asymptotes. And asymptotes are invisible lines along the graph that our function never quite reaches. It gets super close to reaching, but just doesn't manage to reach them, no matter how hard it tries. And today we'll go over why these asymptotes exist, how to find them, and how to deal with them. And this is the properties I was talking about when I was mentioning why rational functions are so interesting. Rational functions are one of the few functions which deal with asymptotes on a regular basis. And they deal with so many asymptotes, we have an entire set of rules for how to for when asymptotes occur, which we'll go over in this video. So, let's start off nice and simple with factoring our original expression. Because frankly, that f of x is way too messy, and it's always lovely to deal with a simplified, clean expression. It makes doing math a whole lot easier. Alright, so I had 2x squared plus 5. Can't really factor that. Over 2 plus x over 2 plus x times 1 minus x. Right, and I just factored that 2 minus x squared, make it a little simpler for me. Right? And I remember back when we were talking about rational expressions. And when we were talking about rational expressions, they were extraneous solutions. Right? If I had a value that I could plug into the denominator and get 0. Right? Like if I had a rational expression of 1 over 2 minus x, right? X equals 2 would be an extraneous solution. Because if I plug that into my rational expression, I get 2 minus 2, or 0. And anything divided by 0 we know isn't defined. Let's try to do the same thing here, right? What values do I have to for x will cause my denominator to be 0? Well, that's really just saying, when is this whole thing, this expression, this denominator, equal to 0? And since we're multiplying by 2 terms, either of these can be 0 for the entire thing to be 0. So we can have 2 plus x equals 0 and 1 minus x equals 0. Doing the math, I have x equals -2 and x equals 1. Now, here's where things get interesting. If I were to go back to my graph and I were to label my asymptotes, I'd have 2 vertical lines. X equals -2 and x equals 1. And those are the exact same numbers as those I found here. Now these are what we call vertical asymptotes. We call them vertical asymptotes because they are just vertical lines that our graph can get really, really close to, but never cross or touch. And they occur just by, and we can find them at least, by taking our denominator, setting it equal to 0, and then solving for x. And each of those x values will be vertical asymptotes, places where our graph will never, never, never touch. But what about this horizontal line, which we can call, of course, a horizontal asymptote? As it turns out, there are pretty specified rules for when we deal with horizontal asymptotes. And let's go over what exactly those are. Right. They all have to do with the degree of our rational function. Right. In this case, the degree is always the highest term, the highest exponent term in a polynomial. So we're looking at the degree of the numerator, which I'll call m, and the degree of the denominator, which I'll call d. Right. And if we distribute this out, we get x squared. So that we have a degree of 2 in both the numerator and the denominator. And here's how the process goes. If the degree of the numerator is less than the degree of the denominator, our horizontal asymptote is y equals 0. Right? It's just a line across our x-axis, which our graph will get really, really close to, but never quite touch. Right? If the degree of our numerator is equal to the degree of our denominator, then we have a horizontal asymptote at the ratio of the leading coefficients. And what that means is we're going to have the number attached to the highest term here over the number attached to the highest term here. In this case, it's 2, because we have 2x squared in the numerator, over -1, because we have negative x squared in the denominator, which is -2. Right? So we have a y-intercept at -2. Which, again, if we look at our graph, is actually the case. Right? So, we also have one final property of horizontal asymptotes. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. There is a slant, or also called oblique asymptote. What is that? Well, before we get quite into what a slant or an oblique asymptote is, it's important to make a distinction between vertical asymptotes and our horizontal or slant asymptotes. Our vertical asymptotes, our graph of any rational function will never be able to cross any of them. But a graph may or may not cross a horizontal or slant asymptote. So at some graphs, it won't cross a horizontal asymptote. In other graphs, it will, just depending on the graph. For example, I could have a graph like this, where we have a horizontal asymptote, let's say, somewhere here, and I have one part that just goes like this, and approaches it this way, and of course, doesn't quite reach it, but it can cross it. Right? Another thing to note, the graph of a rational function may have many vertical asymptotes, because remember, a vertical asymptote is just a point where, if I plug in x in the denominator, I get 0. And in this case, right, I have 2 vertical asymptotes. I could have 3, 4, 5. In theory, I could have a whole ton of vertical asymptotes. But with the rules I have defined, I can only have one, at most one, horizontal or slant / oblique asymptote. But enough of the specifications. What about what is a slant asymptote, and how do we find it? So. Let's say I have the function 3x squared minus 2x plus 1 over x minus 1. And I'm just immediately graph that so I can see what the properties I am experiencing are. my graph looks a lot like this. I notice, hey, there seems to be some line, some straight line that is acting like an asymptote in this graph. And of course, we also have our vertical asymptote here at x equals 1. We get this because we set the denominator equal to 0, and we find out that it's 0 at x equals 1. But how do we find this slant asymptote? Well, for finding slant asymptotes, what we do is we divide out this rational function, and we just ignore a remainder. And the quotient, what we're left with, is our slant asymptote. It's this line that we can't quite cross. All right, so I'm going to do the division here. That's I'm going to just subtract that. That's 3x squared minus 3x. I'm going to read that negative sign out, so that becomes x plus 1, which is of course another plus 1 because I want to get rid of that x. So I have minus x minus 1. I'm left with the remainder of 2. Don't care about the remainder, so I really just have 3x plus 1. That is indeed my quotient, so my slant asymptote right here is y equals 3x plus 1. And that describes my slant asymptote. And so, that's what a slant asymptote is. So we covered our 3 types of asymptotes. Our vertical, our horizontal, and our slant. And we've also gone over how to find them using the equations, the algebra, present in each rational function equation. And through that, we can unlock all the properties of rational functions, and we can graph them nicely and easily. So, I hope you found this helpful, and I hope you have a great day. Thanks for watching.